Okay, in this short video, I want to spend a little bit of wrap-up time just talking a little bit about the final regression interpretations and some of the, we talked about fit statistics earlier, but we also want to think about now the interpretation of the actual betas. The beta coefficient comes in both standardized and unstandardized fashion or returns, if you will. So the unstandardized uh, beta is the weight that we use when we use a regression formula to predict the dependent variable. So if we have a estimated model, we use the betas and we multiply those by the independent variables, and as the independent variables change, the value for the dependent variable changes. So we can use then the weights for the unstandardized weights as a method to predict the variate at the end of the day. So that's what we want to do with those. The standardized betas are used to estimate, or rather than estimate, they're used to tell us significance, to do the significance, to interpret the significance level of the value of the coefficient. So that coefficient, that beta, the degree to which it is not equal to 0 is the degree in which it is, whether it's significant or not, on the standardized beta. The other thing about the standardized betas are those are the ones that we can compare or use to compare independent variables to each other. They're relative to each other because they're standardized. So if one, say, is a 0.5 and another one's a 0.25, then we know that the independent variable associated with 0.5 is twice as strong as the independent variable that's 2.25 in explaining the variance of the dependent variable. So the standardized betas then are what we will use to recognize the relative importance among the independent variables. Other things that we have looked at already deals with multicollinearity. So again, when multicollinearity is in existence, it dampens or hides the true value of the beta that's associated with each independent variable. So it has an impact of suppressing then maybe the true effect. So if multicollinearity exists, if we can take out the variables that are multicollinear, then it'll actually help the model fit overall. It's obviously multicollinearity is viewed as a damaging type of a thing, but understanding that it masks the full effect of a variable may actually bolster some of your interpretations of the impact a single variable may actually have. We know that multicollinearity again reduces R square, and again it confounds the estimation of the regressed coefficients. So that's what we want to be able to think of in terms of interpretation. So we talked about multicollinearity before. We talked about tolerances, and we talked about variance inflation factors, and we want to try to correct for those as well as we can. We also know that correlations, I suggest above 0.7. Others say even higher than that, but we know that that's a value that can be a challenge, if we don't correct for it. So we've talked about multicollinearity in the past, but so this is really kind of the point in which we're interpreting the results, looking at a histogram and looking at the normality normal probability plots, normality plots, help you identify how well the observed the observed results match up with the predicted results. So a lot of times we'll have standardized residuals, and then we'll have the observations, and this line, what we have here should hug this line very closely. Sometimes we'll have a situation where the data will do something like this, and that would suggest that we have non-normality taking place in some of the variables, and we have to go into the variables and try to normalize them if we can. So that would be something that we would think about doing there. The scatter plot of the residuals is another option where we'll have all the residuals scatter plotted out with its expectations, and we typically see this on a scale, on two scales, based on maybe degrees of freedom, or not degrees of freedom, but standard deviations, and we want to look for things that are like way outside these marks here to be potential outliers or variables that would be unexpected within the scatter plot. We would look for a random pattern with no identifiable violations. But if we see where there's a pattern of data, or whether there's data outside extremes here, then we know we have some potential problems that exist. Okay, so take a look at the videos that walk through regressions. Those will sum up the different steps that are needed to do a regression analysis. Thanks.